I'm just using the correlation coefficient to save myself from plotting. The closer this value is to 1, the better the choice would be. If you do choose to graph and just hit the graph key to show that graph, it's going to end up showing you what the graph ends up to kind of come up a little bit like this. Whoops, I'm not showing it on the screen. So what we're looking at, where the natural log of A set over time is giving me a negative slope, but it's showing a curve. Let's try again a linear regression, but we'll use the second set of data, time versus the reciprocal. So stat, calc, linear regression is choice 4. I want to do list 1, comma, list 4, and see what information I have. The R squared is 0.99998, so forth. You can see the R squared, best I can, I'm trying to show that, 0.9999. When I graph this, if you choose to show that to yourself by actually visualizing the graph, you get a straight line. 1 over the reciprocal of A set over time gives me a straight line. I simply choose to look at the R constant. If it's close enough, I might have to choose to graph for visual effect, but I rely on the calculator to do the hard work for me and save myself from graphing. This is definitely showing a better correlation to a second order reaction. This set of data shows a straight line with list 1 in time, list 4 is reciprocal. Therefore, we know that the best choice is first order. Excuse me, second order. I circled the wrong answer. Second order. So, a couple of interesting things. Y equals mx plus b, where, of course, the slope of the line is the rate constant. You can pull that right from your screen as well, where mx plus b, and you can find what we call a for m. There's the k constant right on the calculator screen. You can see it here. So the k constant can be found at the same time you're graphing. Now I'm used to saying y equal mx plus b. This calculator is ax plus b, but that's the slope of the line. So this value from the calculator is giving us the k, the rate constant. Practice this. Consider again the decomposition of NO2. The reaction is second order with respect to NO2. The K constant is 0.543. Notice that's exactly what was on our calculator screen a moment ago for that, the slope of the line, the K constant, 0.543. So again, that's verified in the next part of our problem to match the second order choice. If it's second order, the molarity to the -1, second to the -1 makes sense for that rate constant, doesn't it? 1 minus the overall. If the initial concentration of NO2 is 0.05 molar, what is the remaining concentration after 0.5 hours? There's a little trick here. 0.5 hours, half an hour, but the rate constant is in a per second. So consider that as we're getting ready. 0.5 hours matching into the per second. Here's what I know. There's 60 minutes in an hour, and there's 60 seconds in every 1 minute. So I'm converting half an hour into the number of seconds when I do that. 0.5 times 60 times 60 is showing me, not that, excuse me, try again. 0.5 times 60 times 60, I get 1800 seconds. So the reason I did that, when I plug into my formula for second order rate law, I want the rate constant time to match the time that I place in the formula. Second order says the rate of the concentration of a reactant over a certain time interval is kT plus the reciprocal of the original concentration. It's plug and chug. Let's see what we find. Here's what we know. The rate constant, 0.543 molarity and seconds to the -1. The initial concentration in a closed vessel was 0.05 molar. The time we determined to be 1800 seconds. How much of that is left after 1800 seconds went by? I think I'll choose to start with the right-hand side and simplify. 0.543 times 1800 equals plus parenthesis 1 divided by 0.05. 1 over the original concentration, or excuse me, the concentration remaining after these 1800 seconds went by. I'm seeing on my screen 997.4. We want to pull this out. So the algebra would show that these two values just simply switch numbers. We're going to multiply both sides by that concentration of A and then divide both here. So just to rearrange this, I'm sure that the algebra would be friendly. What we end up doing is 1 divided by 997.4 equals that concentration of A at that remaining time, A representing that NO2, the decomposition reactant. Going back to this part, we're trying to solve here, knowing this value, in your head just flip those. That's what the algebra will show. 1 divided by the answer still on my screen. 1 divided by 997.4 gives me an answer of 0.001 molar, the remaining concentration after 1800 seconds. Check to see if it makes sense. The original concentration 0.05, this value is smaller. That makes sense. Reactants get used. A lot of time went by, so you got used up a lot. Let's pause.